Hello, and welcome to our presentation on neutron scattering techniques. So, let's get started, shall we? First of all, we're going to talk about some basic theory. To start, the basis of elastic neutron scattering is fundamentally no different than that of other diffraction processes, such as the various forms of light diffraction. Just like all other quantum particles, neutrons can be described from both a particle and a wave-like perspective. In this case, the wave-like behavior of neutrons allows it to experience the phenomenon of diffraction, typically associated with only light, which is more naturally thought of from a wave point of view. Neutron scattering, in its simplest form, provides a direct measure of spatial and temporal correlations of atomic positions and magnetic states of the target system. Therefore, the theory of neutron scattering allows the physical quantities to be calculated beyond the scattering itself. The reason neutrons are so adept for this type of research is that due to their lack of an intrinsic charge, they can penetrate matter not hindered by Coulomb forces like other charged particles would be, such as protons, allowing them to reach further areas in subatomic matter for study. However, there is a very specific type of neutron that is required for this area of research, and these are called thermal neutrons. Now, thermal neutrons are created by pushing the neutrons through the moderation section of the research reactor, usually using water, heavy water, or beryllium as their moderator. This is to slow the electrons down to the point of collecting them and being able to use them. Some research facilities also require the neutrons to be even slower, so the moderator becomes something such as liquid hydrogen or liquid helium, some of the coldest temperature liquids on the planet, to achieve cryotemperatures of under 20 Kelvin in order to reduce them to the energy states required for testing. The image on screen is a basic schematic of an inelastic neutron scattering setup, featuring a neutron pulse, a monochromator, a monitor, the sample being measured, a beam stop trap, and an analyzer and detector. Now, the only thing you're probably not familiar with on this slide is a monochromator. This device is specifically made to split neutron wavelength from other particle wavelength in order to isolate and capture them ready to be used, so that only the sample is being monitored by neutrons. The way it functions is by creating a beam of neutrons and passing that beam through whatever sample or object is being measured, and then noting where, or possibly when, depending on what you're measuring, the neutrons scattered hit a detector. One possible way of creating these neutrons, apart from a reactor, is by colliding protons with a heavy metal such as tungsten or mercury in a particle accelerator in a process called spallation. The main type of scattering for neutrons is regarded as being elastic, as they are elastically scattered by colliding with the nucleus of the measured atom. Moving on, at least the basic part of it, we're going to move on to some instrumentation. The basic concept involving the instrumentation is that a charge-free beam of neutrons is passed through several wavelength and particle filters to isolate solely the thermal neutrons required for the process, as per the monochromator we mentioned earlier. This beam of neutrons is then passed through whatever sample is being recorded. The scattered neutrons are then monitored as they disperse and are collected by a transmitted beam monitor. There are usually several analyzer banks present commonly, using materials such as graphite for moderation. As well as analyzer banks, there are always diffraction detectors that collect a lot of the main information about the scatter patterns. There are many different types of instruments and detectors associated with neutron scattering, depending on the type of study and results that are wanted. Here are some examples. So the one on screen right now is currently called IRIS. The detector on screen is called IRIS. It's an example of one of the many types of neutron scattering devices. This one is a time-of-flight inverted geometry crystal analyzer designed for quasi-electric and low-energy inelastic spectroscopy. It measures energy differences via something called Bragg reflection. Now, on the image, you can clearly see what was mentioned before, being the graphite analyzer bank, the transmitted beam monitor, which is what actually collects the neutrons afterwards, some diffraction detectors, and the cryostat that keeps the whole device under 20 Kelvin to be measured. Another type of detector is called Larmor, which is the second image on screen. Now, Larmor is a special type of spectrometer that is flexible to multiple different uses of neutron scattering. However, its most used and main function is called SANS, or small angle neutron scattering. This process is a more refined scattering technique that measures diffractions and energy level differences on the nanometer scale, 1 to 100 to be specific. Since this has a much more detailed set of apparatus, it can provide detailed studies of long-range structure and interparticle interactions in colloidal dispersions, foams, lamellar fragments, supramolecular conjugates, complex mixtures, composites, templated and phase-segregated systems. These have potential applications in areas such as photonics, drug delivery, gene therapy, catalysis, separation science, and next-generation materials. And that's a lot more. Now, the next slide is going to be presented to you by Lainey, and it's going to be on the advantages and disadvantages. One specific type of neutron scattering that is used in a wide range of spectroscopy is inelastic, the opposite to the elastic just mentioned. This involves measuring the change in energy specifically when the neutron scatters from a sample. Some of the different physical phenomena that are measured are diffusional or hopping motions of atoms, the rotational modes of molecules, sound modes and molecular vibrations, recoiling quantum fluids, magnetic and quantum excitations, or even electronic transitions in terms of the elastic form. The image on screen right now is a high-flux isotope reactor, which provides one of the highest rates of continuous beam neutrons in the world. This is one of those research reactors that I mentioned earlier, currently performing the moderation part of the neutron scattering. Collisions between the neutrons and the atomic nuclei in specifically elastic can cause atomic motion within the material lattices. This will then cause the neutrons to transfer their energy to the matter. This is how the energy states are measured, as when the neutrons transfer their energy to the matter, they're able to be recorded in the change. By measuring and detecting these energy shifts, much information can be determined and gathered about the fundamental atomic structure and motions taking place. So, now that the theory is all covered.
There are many advantages to neutron scattering. It is a non-destructive technique, since neutrons have no charge and thus mostly travel through the subject without interacting. This is useful as some of its applications include medicine and food processing. It can also be used to analyze materials with both heavy and light elements, when compared with X-ray or electron diffraction, which can only be used for heavy elements. This is especially useful within the structural biology field, since it is sensitive to the structures of many biological molecules, like proteins. The high penetration power allows for the inner structure of materials to be studied, including while under extreme conditions such as high strain or compression. Neutron scattering also allows for the identification of different isotopes, since they all have different scattering lengths. One of the most important examples of this is for hydrogen and deuterium, which is used when studying water or hydrogen-containing materials, making it again very useful for biological studies. Some disadvantages include the instruments being sensitive to background noise. They're expensive to run. One paper stating a machine could cost between 10 to 20 million euros. And because neutrons scatter weakly, they can be difficult to detect. Neutron scattering occurs when neutrons are rejected, hit the subject, and are then dispersed. This happens following Briggs' law, which is essential to determining the subject structure. This is Briggs' law, where n is the integer of reflection, lambda is wavelength, and d is the plane spacing. Using the wavelength of the neutron, the scattering length can be calculated. This can then be used to work out the scattering cross-section. This is the equation of the cohesive cross-section, and this is the incohesive. The overall equation is for the differential scattering cross-section, where the absolute value of b is squared and times by the absolute value of the sum of e to the power of ikrn squared, where b is the mean scattering length, k is the scattering vector, and Rn is the position of the vector of the analysed atom. N times the absolute value of b minus b squared is then added, where N is the total number of atoms in the structure. Here is an example of the two isotopes mentioned earlier. You can clearly see that both the scattering length and the cross-sections are vastly different, allowing for easy identification. Thank you for listening to this presentation on neutron scattering.